In today's lecture, we're going to have sort of two parts. The first part, we're going to look at something that we really haven't talked about at all yet in the course, but that we'll be coming back to in a couple of subsequent lectures. And that's interactions between the particles in our system. So we've talked about that the system is interacting thermally with a bath or interacting chemically, exchanging particles with some bath. But in something like an ideal gas, we assume that the atoms never run into each other, or the molecules never run into each other. When we try to talk about Bose-Einstein condensates in the lab, we really can't avoid talking about interactions. It sort of dominates over a lot of the sort of things we usually think about. So I'm going to take the opportunity to introduce both just a general concept of how we think about interactions, but specifically a technique called mean field theory. And that may sound intimidating. It's really not so bad. And we'll come back to it again later on when we talk about spin systems toward the end of the course. So getting you introduced to this as well. Then, after we've talked a bit about this, we're going to switch gears a bit, and I'll run you through some slides talking about sort of big results in Bose-Einstein condensation. This could easily be an entire course, so it's necessarily going to be very brief and schematic, but I hope you'll enjoy getting to see a bit of what goes on in modern research in this area. Echo came down and was crying. I think she wanted to be sure her fans get to see her at least once every couple of weeks. Also, I don't think the microphone's picking it up, but there's a ton of construction outside my apartment, so I apologize if you hear this sort of jackhammer kind of sound in the background. Okay, so what I want to talk about here is both, and I guess I titled this backwards, first the BEC wave function, just as a concept, and then how it fits into the idea of mean field theory. So to start with, let's talk about many body wave functions. Okay, we've mentioned this briefly in talking about statistics. We said the wave function for two fermions has to be anti-symmetrized in the coordinates, and similarly the wave function for two bosons needs to be symmetrized in the coordinates. So we have, hopefully some idea from your quantum mechanics course that when we go from a single particle wave function, describing a system which is a single particle, to a many body wave function, we now have a wave function that is a function of all of the coordinates for every particle. So if I was describing a classical system of particles, I would go from 3 coordinates, or really 6 if you want to describe it in phase space, right? You need position and momentum, or position and velocity. I'd go from 6 coordinates to 6 times n coordinates. It's just a slightly, not slightly longer. It could be a much longer vector, but it's still just a vector. In quantum mechanics, we go from a function over 3 variables to a function over 3n variables. And if you're talking about the sort of the size of the object, if you think just like, I want a computer to contain an approximation of the wave function. This is now going from something that looks like maybe if you wanted 1,000 points per coordinate as your discretization of space. On the left here for a single particle, this is 1,000 cubed points. Over here, this is 1,000 raised to the 3n. And if n is 1,000 particles, you've got 1,000 raised to the 3,000. This is a humongous number. You'll never, ever get this into your computer memory. Okay, Echo, I'm afraid you're just a little too distracting. Down you go. Okay. Good. So this is one of the reasons people talk about quantum computing, is that the wave function, as your system grows, the information content in the wave function grows exponentially with the system size. Whereas in a classical system, it just grows linearly, right? If I've got 100 atoms, I've got 600 coordinates. If I've got 1,000 atoms, I've got 6,000 coordinates. Whereas, again, the information content of the wave function grows exponentially. And the idea is that you can use that exponential growth as a resource for computing, as opposed to looking at it as a burden when you try to do classical computations of many-body systems. Okay, so this is your many-body wave function, and this is, well, I haven't told you much about it except that it's a function of this large number of variables. Now, usually this thing is tremendously complicated and we just don't want to deal with it. Sort of like a cat who really wants to get on your desk. You just don't want to deal with it. So for a BEC, it turns out we can make a very, very nice approximation that simplifies this thing dramatically. So probably you're not used to thinking of functions over spaces of 60,000 variables or 30,000 variables if we've got 10,000 atoms, right? Much less a million atoms, which we will talk about. So instead of a function over 3 million variables that could just sort of have an arbitrary form, we think about what is the physics of Bose-Einstein condensation. Okay? The physics is every atom in the system drops into the ground state. Okay? Another way to think about that is to say every atom on its own has the same single particle wave function. And for bosons, we can construct a totally legitimate many-body wave function. And by legitimate, I mean it has the right exchange symmetry, right? If we swap two coordinates, it doesn't change the wave function. We can do this, hopefully. We can do this by writing our many-body wave function as a product of identical single particle wave functions. Okay? So we said the physics is all of the atoms go into the ground state of the system, the single particle ground state. Great. Their wave function should just look like everyone in the single particle ground state. So this phi here is going to be the ground state wave function for a single particle in our system. So this you can just sort of check for yourself. Yeah, if I swap coordinates, it doesn't change anything because I've got a product over phi on every coordinate. So swapping coordinates doesn't change anything, right? Multiplication commutes, at least for regular functions. Good. So this simplifies things dramatically. It fits with our intuition about what Bose-Einstein condensation does as a phase transition. Everyone goes into the ground state, so everyone has the same single particle wave function. And if we ignore interactions, that sort of tells the whole story. We can reduce the whole description of a BEC into solving the single particle Schrodinger equation. Okay, that would be super easy. And then we could do sort of what I hinted at in the last lecture, which is we have thousands or even a million atoms, even millions, of atoms, all in the same single particle wave function, which means when we interact with them, each one behaves as a single atom should. But then when we detect them, the detection sees 10,000, 100,000, a million atoms all at once. Okay? So it's as though we did a million different experiments with single atoms, always the same experiment, because we're quantum mechanics, we need to build up statistics to get the shape of the probability distribution. Here we can do all million experiments simultaneously. This sounds great. It is great. But interactions do change the picture quite substantially. Okay. So the new idea that we need to work with this many particle wave function is mean field theory. Okay. So not mean in the like Professor Jameson writes all these problem sets with zeta functions in them. Not that kind of mean. This is mean as in the average. Okay. So it's just an average field theory. Not so bad. No. Okay. So what we're dealing with here is the average field created by all of the atoms at once. Okay. So if every atom has the same single particle wave function, then I can think of my BEC as just a collection of atoms, all with identical wave functions, which if I was a decent artist, these would look identical. Or if I had used the copy and paste function, which I now realize I should have done. Anyway, ignore the fact that I'm not a great artist and assume these are all identical. Then I can describe the situation by saying, if I think of one atom, I'm going to pick out this blue one, pretend it's special, but it's not. They're all indistinguishable. If I just think about this one atom, and it's interacting with all these other ones, okay? So I've drawn little red arrows here to show you, yeah, it interacts with this one and this one and this one. And I've just stacked them vertically just to space them out so you can see how many atoms there are. Realistically, they're in the same wave function. They're all in exactly the same position distribution. Okay. But so this one is interacting with all the other ones. And what mean field theory says, average field theory, says just think about the interactions averaged over all of them. If they're all identical, they should all do about the same thing. And so instead of trying to deal with each individual interaction, I just say, well, this interacts with one atom in the same wave function, and its interaction strength is n times bigger than it would have been if it was really a single atom. Okay? So I can take the great number of interactions I have and reduce it down, just treat it as an n times stronger single interaction. Okay? And now, how do I describe the interactions between atoms? When we're looking at ultracold atoms that we make a BEC out of, you can describe the interaction simply as what's called a contact interaction. So if two atoms bump into each other in the same position, right? So we've got a delta function of xi minus xj. So when xi and xj are identical, two particles are at exactly the same spot, then they interact. And they interact with a strength that's controlled by this little alpha out front. So alpha is just some constant. Depends on what kind of atoms we're looking at, whether they're sodium, lithium, ytterbium. That'll control the size of alpha. But the form of the interaction is always the same. It's just a contact interaction. Okay? So if I'm wondering what's happening to this atom, it's going to depend on the density of the other atoms at that position. Now, we want to take this wave function and use this idea to come up with an equation to describe it. Now, it's a wave function, so, well, it should, obey the Schrodinger equation, right? You've seen this guy before. Got a time derivative, you've got the kinetic energy term, right? Minus h bar squared over 2m times the Laplacian. This is the kinetic energy of the wave function. You've got a potential energy term, right? Whatever your potential that you're sitting in looks like. And now, to deal with these interactions, I've added a third term. And I didn't add it. Mr. Gross and Mr. Pitayevsky added it. This is called the Gross-Pitayevsky equation. What this term does is it says, hey, look, I've got this interaction whenever things are sitting on top of each other. And they're all identical. So I can, instead of summing over n factorial or n squared interactions that look like this, I can just say, hey, I've got n atoms, right? They all have the same density distribution, right? So if I take the modulus squared of the wave function, that gives me the density. You would say in your regular quantum mechanics course, it's the probability to find an atom at a certain position. And that's true. But if I have n atoms, I can kind of look everywhere. And once I take those probabilities and multiply it by n, it gives me the total density. Okay? So I'm going to have an extra potential energy, right? Something times phi looks just like this term. But instead of saying I'm in a potential that looks like, say, a half m omega squared x squared, right? So your harmonic oscillator potential, something times x squared is a harmonic oscillator. So instead of having that kind of potential, or I'll say in addition to having that kind of potential, we have a potential that's made by all of the other atoms who are all identical. So the phi is our single particle wave function for everyone, which means the density looks like phi squared times n. Okay, the probability to find an atom in any given place times the number of atoms we could potentially find there That's our density. And then, again, this little coupling constant out front that controls the strength. So we've got alpha times the density. That gives us an effective potential due to all of the other atoms. And we can, if we want, we can call that the mean field potential. Okay. So if I take this and wrap it up and just write it like so, you'd say, oh, yeah, it looks just like our other potential energy. The difference is this potential energy depends on phi. Okay. So cover this term up and you just have the regular Schrodinger equation. It's a linear equation. You can solve it with a lot of standard techniques. Once you add this term, because the potential itself depends on phi, this is a nonlinear equation. And this could be an entire course. How do you solve this thing? And since it could be an entire course, I'm just not going to answer. There's a lot of numerical techniques for simulating this equation that allow us to simulate our experiments. But trying to teach you how to solve this equation, definitely beyond the scope of the course. So why am I showing it to you at all? Well, first, because now you can tell all of your friends, oh, you do that linear Schrodinger equation? That's nice. I use the nonlinear Schrodinger equation. But of course, if you only have one particle, you should not use the nonlinear Schrodinger equation because there is no mean field interaction. Okay. More importantly, there is in fact one case where you can solve this equation quite straightforwardly, and it turns out it's super important to studies of BECs in the lab. So I'm going to let you do that on the homework. And on the homework, I'll give you the setup so you'll know what you're doing. Let me just say one other thing here before we move on to modern stuff in the lab. This Gross-Pitayevsky equation is very fundamental to extracting meaningful information from almost any experiment in the lab. This is the time-dependent Gross-Pitayevsky equation. Just like in your quantum mechanics course, you saw the time-dependent Schrodinger equation. And you also saw the time-independent Schrodinger equation, right? You said, hey, if my wave function is an eigenstate, then this time evolution is just, it winds up phase based on its energy, right? So when I take the time derivative, I'll get minus I energy over h bar, right? That's the rate at which phase winds up on an eigenstate. And then the I cancels and the h bar cancels. So you've really just got the energy over here. Okay. And that's your eigenvalue for your eigenstate of the Hamiltonian. There's a similar kind of thing, although because this is nonlinear, it doesn't have real eigenstates and all of that machinery falls apart and it's terrible. We just have to do a lot of things numerically. But conceptually, you still have a time-independent Gross-Pitayevsky equation, and the time-independent Gross-Pitayevsky equation looks just like your time-independent Schrodinger, except instead of E here, the energy of your single particle state, we have mu. And yes, this is our old friend, the chemical potential. Because if every particle in the condensate has the same single particle wave function, then the energy of that single particle wave function is your chemical potential. Think back to the definition. Chemical potential is the energy required to add a particle to the system without changing the entropy. Okay. And for normal classical gases, it's negative, right? Because if I add an extra particle to the system, there's more degrees of freedom. I've increased the entropy. I have to take some energy away to keep the entropy constant. With a BEC, the story's opposite. A BEC has no entropy. Every particle is in exactly the same state. There's only one microstate that describes this macroscopic state, right? So when you count, the number of ways to make this thing, there's only one. Log of 1 is 0. So the entropy of a BEC is 0. If I add another atom to the BEC, it's still 0 because it's still a BEC. Okay. So the energy required to add one particle to the system without changing the entropy is just the energy of a particle in the BEC. So this thing that's analogous to the energy for a single particle wave function turns out to be our chemical potential. Okay, great. So you can use this time-independent Gross-Pitaevsky equation to figure out the situation at the beginning of an experiment, right? We've cooled stuff, we've made our BEC, and now we want to do stuff to it. But before we do stuff to it, we want to know, what did it look like to begin with? In other words, we have a stationary state BEC, and while it's not, again, it's not an eigenstate because this is nonlinear, it is a stationary state. It stays the same forever. We can use this time-independent Gross-Pitaevsky equation to solve for the starting wave function of an experiment, and that's what you're going to do on the homework. And again, this equation looks awful because it is, but there's a very nice approximation that will allow you to solve this on the homework. Okay, last thing I want to say, n times mod wave function squared. We talked about this up above, right? This is like the density times some coupling constant. The density, though, is a function of position. So I just want to emphasize this because in the past we've just talked about density in the context of atoms in a box, right? And we have the same density everywhere because the box is the same everywhere. Right? So we have had little n equals big N over V, right? The number density. We've always just had that as a constant. It's the same anywhere in the system. For an interacting BEC, that's no longer true. The density is not a constant, it's a function of position. Okay? And so that'll be an important thing to think about when you solve this homework question. Okay, so I think that gives you the idea of mean field theory, right? Just saying, hey, if all the atoms are identical, then one should feel an interaction that looks like the average over all the others, which is to say just n times the single particle density, right? Single particle density times n is our total density. That gives us our interaction string. Good, so I'm going to switch over now to some slides, and we'll talk about some exciting things that have been done with BECs since they were first observed in 1995. If you watched the Not a Lecture video that I posted last week, some of these slides will be familiar, but I want to talk about them in a little more depth than I could in a talk that's aimed at the general public. Yes, so let's get into it. If you watched that, you learned a lot about laser cooling, which is how we get our atoms in the lab down to something like 10 microkelvin temperatures on that scale. But the Bose-Einstein condensation transition in our systems happens at even lower temperatures. How low? You'll calculate it on the homework. Lower than 10 microkelvin though. There's a good hint. If you come up with 10 millikelvin, you've done something wrong. So we can laser cool to 10 microkelvin, and then we need another technique to cool further, which is called evaporative cooling. And the picture that I have here is if the shape of my potential is like this, and frequently we use potentials in the lab that are shaped not exactly like that, we'll call it non-artist's rendition. At the bottom, it looks like a harmonic oscillator. So you've got evenly spaced energy levels, right? And then toward the top where it levels out, the energy levels get closer and closer together. And we're usually working in the situation where our atoms are cold enough that almost all of them are at the bottom, where it's very, very harmonic to a very good approximation. But in the process of cooling them, we have this situation sometimes where the atoms are spread out across all of these energy levels. Everything that's trapped is possible. Now, what we do to cool is we just, there we go, we make the potential shallower. So if we make the potential shallower, suddenly these top two atoms aren't trapped anymore, which means they're going to fly out of the trap. And since they were the two with the highest energy, the average energy per particle has gone down. Now, interesting story, it doesn't mean the temperature's gone down yet. In fact, there isn't a well-defined temperature right now. Okay, the probability distributions here look like the probability distribution at a certain temperature, except the high energy tail of the distribution is gone. Okay, so it doesn't look like a thermal state. We can't define a temperature for it. We can define an energy per particle, and from that we can calculate what temperature it would be if everything were thermalized back to a thermal probability distribution, right? But if we're being really precise, very careful, there isn't a properly defined temperature here. Okay, but we lose a bunch of energy. We reduce the energy per particle, and then collisions inside of the gas will relax it back from this non-equilibrium state we've put it in into thermal equilibrium, which is to say it'll come back to the right shape probability distribution for the energy per particle that it had at equilibrium. Okay, and in the process, it has to regrow this the high energy tail, and so maybe another atom gets kicked out when it catches too much energy. Okay. So now we've got a gas that's actually, once it's thermalized and we can define the temperature, it's at a much lower temperature, right? The way I refer to this a lot of times is these atoms took more than their fair share of the energy, as did this one, which is good. That means our energy per particle is lower, and once we've regained equilibrium, regained a thermal distribution, the temperature we would measure is much lower. Okay. So this is a very efficient way to cool things. In the NADA lecture, I talked a lot about laser cooling. Just wanted to give you, and I tried to make it very simple in that case, and I wanted you to get some idea of what an ultra-cold atoms lab actually looks like. This is the lab that I did my postdoctoral work in. You can see there's some nice colors, these red and yellow colors. That's how you laser cool sodium and lithium. We got a lot of electronics going on here. Control computer for controlling the whole thing. This is only part of the lab. There's even more lasers lying around. These are infrared lasers, so they don't look very exciting. Here's that nice sodium yellow. You see a little bit of this lithium red. Anyway, so these experiments take some time to build up. But it's worth it because of all the cool things we can do once they're built up. So one of the, let me talk about Bose-Einstein condensation again. Again, this is slides that you saw already in the NADA lecture video. If we think of atoms in a box or atoms in a simple harmonic oscillator, either way, as we cool, this thermal de Broglie wavelength is going to get bigger, right? And thermal de Broglie wavelength here, we've seen this many times now in this course. And this, we've also seen many times, this is the phase space density, right? So big N over V is our number density, times the thermal de Broglie wavelength cubed gives us our density in position and momentum space, right? The number divided by our volume in position space, and this thing is really 1 over the volume in momentum space. The other way I described it in the last lecture, this is the number of particles per coherence volume, right? If we put the big V in the bottom, big N in the top, this is thermal de Broglie wavelength cubed is our coherence volume. So that over V is the number of particles divided by the number of coherence volumes. Okay. And now you can sort of see in this picture, this is the coherence, area because it's a 2D picture, but you get the idea. This is our coherence volume, and I could draw another square over here that's the same size, and it's empty. And I could draw one here, and it's empty. So the way this picture is drawn, are N over our number, so number of atoms over our number of coherence volumes, it's maybe half, okay? That's actually quite large phase space density, but it's still less than 1. Okay, so we still don't have a BEC. And if you were in the different situation of a harmonic oscillator, which you'll consider on the homework, and let me say, you'll consider on the homework because almost all of our experiments start in a harmonic oscillator potential. If you remember at the end of the last lecture, I showed you two papers. One was the very first observation of BEC from 1995. That was in a harmonic potential. And then, what was it, 17 years later, in 2012, I showed you a paper of the first BEC in a uniform potential in a box. Okay. So this is going to be a very important situation for experiments. Now we increase the phase space density. Once it's essentially 1, I can't really draw a coherence volume that doesn't have an atom in it. Okay? So these are now starting to overlap in their coherence volumes, which means that they can start to interfere with each other. And one of the reasons I wanted to touch back on this, as compared to what I was able to say in the public lecture, is during this dynamic, we're going to see something like that Hong-Ou-Mandel effect that I talked about a few lectures back. When we first introduced fermions versus bosons, I talked about this Hong-Ou-Mandel effect, which is if I send two identical bosons, maybe it's two photons, onto a beam splitter, and it's a beam splitter that would normally, if I send one photon, it's got 50% chance to go this way, 50% chance to go that way. If I send two at exactly the same time, then either they both go this way or they both go that way. Okay? And that turns out to be due to this requirement that the wave function be symmetrized. Okay? In the context of more than two bosons, this same idea is referred to as bosonic stimulation. And what it says is, right as I'm starting to make a BEC, let's say I've got 10 atoms in the ground state. These two are going to bump into each other. When they collide, they're going to leave with some different momentum. And because they're all at very low temperatures, there's only a few places they could go. And if one of those places is into the BEC, then that will be more likely by a factor of 10. Okay, so because of the symmetrization with the 10 atoms that are already there, you get a higher probability to land there. Okay. You can think of this also in terms of these energy levels at a harmonic oscillator, right? If these two atoms collide, they have to conserve energy, right? So the total excitation energy has to be 1, 2 plus 1, 2, 3, so 5, right? When these two collide, they have to end up in states that add up to 5, but it's twice as likely that one will end up in this state or this state as opposed to, say, this state because of this bosonic stimulation. Good. And then you know what happens. Once we cool even further, we get to high phase space density, we have essentially everything falls into the ground state and we get this Bose-Einstein condensate wave function. This is the thing that you've seen from this discussion of the n integral in the last lecture. Okay. And then I also showed this in the public talk. Interference is one of these hallmarks of quantum mechanics, right? Young's double slit experiment proves that light is a wave, and then it gets complicated. But interference is definitely a hallmark of waves. And I showed you this idea that a BEC gets split into two pieces, and this is analogous to sending coherent light, right? So actually, maybe let me step back. I'm not sure if this was described well in your optics course. Why is there one slit here? The answer is because Young didn't have a laser. Okay? So passing incoherent light through a very narrow slit makes it come out as coherent waves. Okay? So this was his way of making a 18th century approximation of a laser. So once you have coherent light, then you send it through two slits and you get this interference effect. Okay? I want to say that just because if you took a light bulb at home, cut two very narrow slits in a piece of paper, you're not likely to see an interference pattern because the light from the light bulb is incoherent. It's also many different colors, which is a problem. But if you put it through a filter and then put it through a pinhole and then put it through two slits, you could see this interference effect. Okay? Or you do what we do in the lab, which is buy a laser, and now you're already at this point where everything is single color and coherent. A BEC is the atomic equivalent of a laser, right? In a laser, every photon has the same phase and frequency. In a BEC, every atom has the same wave functions in the same state. So this is already coherent. We just need to split it, and now it's like two slits. And when we let it go, they'll expand and overlap with each other, and you get this interference pattern. This dark bands are places with high atomic density. Light bands are places with low atomic density. I also mentioned this kind of experiment in the last lecture where we talked about that BEC in a box. And at the end of the paper, they showed, we cut it in half. We turn everything off, and the two pieces expand, overlap, and you get these interference patterns. Okay? This one is sort of special because this is the first published interference pattern from a BEC. And look at this length scale. This is a quantum effect that you can see on a millimeter size scale. And again, this is just a picture taken with a camera that's just a souped up version of your cell phone camera. Now, things that you haven't seen before. This is a much more complicated interference effect with BECs, right? So seeing this is cool, right? It shows the wave-like nature of atoms. That's pretty neat. But as people will periodically ask me, what's it useful for? What's the good of it, right? And the good is it's awesome, but okay, there's a second good, which is that these interference fringes, actually their spacings and positions, can be extremely sensitive probes to measure various things, like acceleration, which might be interesting to you if you were steering a submarine, right? Underwater, you can't just look up and say, there's the North Star, I know where I am. You have to have some other way. And really precise acceleration measurements, you can just sort of do what you would think from freshman physics. I've got an acceleration, integrate it twice, I know where I am. So interference of atoms can actually make super precise measurements of accelerations. It's also a good thing to do if you're looking for oil, because pockets of oil change the local gravitational acceleration. And so if you're measuring acceleration due to gravity, you can fly around and see, hey, it dropped slightly there. What does that mean? Could mean there's oil. So that's how I justify my existence to people who want to know why my experiments are useful. Another thing that you can measure, and this was actually my thesis work, is the mass of a single atom by looking at its interference effect. Now, this experiment's a bit complicated. I'm just going to give you a very broad strokes overview, but the idea is trap off means I've made a BEC already. It's in this harmonic potential. I turn off the harmonic potential, and now the BEC starts to expand out. This is showing a laser pulse, a short laser pulse. So time is increasing as we go down this axis. The short laser pulse is put together just right so that it puts each atom into a superposition of 3 momentum states. One that moves left, one that moves right, and one that stays put. So each atom is in this superposition of 3 momentum states, and momentum connects to velocity. So if we wait a little while, they're also in 3 different positions. But again, each atom is in a superposition of 3 different positions. Okay, the 2-slit experiment, you'd say you go 2 positions, now it's 3. Great. We do another laser pulse that reverses the momentum of the outward ones so they come back together. And when they come back together, we get an interference fringe. But because we've got 3, we actually get this funny interference fringe that as a function of time, you see fringes and then no fringes. Fringes and no fringes. And what's really happening is these 2 paths interfere to make fringes. These 2 paths interfere to make fringes. But the fringes have different velocities, and so they're passing in front of each other. Okay, so no fringes visible, though they're secretly there. Fringes again. No fringes visible, fringes again. The way that modulates in time actually tells us about the mass of an atom. And this can be used to measure the mass of an atom to better than a part per billion precision. Okay, so if your bathroom scale had part per billion precision, then if 1 hair fell out while you were standing on the scale, you'd see the number change. Okay. So these are extraordinarily precise techniques. And at the end of the day, what we measure is how big these fringes are as a function of time. So you see fringes, no fringes, fringes, no fringes, fringes, no fringes. Okay? And by tracking the period of this oscillation very precisely, we can measure the mass of an atom. Now, I haven't told you enough to go do the experiment, so what's one of the take-home messages here? First, we can make cool movies. Here's what the experiment actually looks like. I said we turn off the trap and that drops the BEC, and it's got mass. It's going to fall under gravity. So it falls, we hit it with a laser pulse that puts it in a superposition of 3 momentum states. You can see those 3 momentum states physically separate. We do that second pulse, and those 3 come back together. We play it one more time. Right? So right now, each atom in this BEC is in a superposition of 3 different position states. Okay? Is the atom here, here, or here? The answer is yes or no. Okay? There's a probability distribution thanks to the wave function, but in fact, they're in a superposition of all 3 states. Okay? And the little wings that come out at the end are just because this is from early on in the experiment when we weren't very good at tuning our laser pulses. Okay, so that's how it happens. And what I wanted to show you is, why is a BEC so useful? So I said a BEC is kind of like the atomic equivalent of a laser, right? Everyone's doing the same thing. It means we get dramatically better interference. So this is the momentum distribution of a thermal cloud just above TC, just above the critical temperature. This is the momentum distribution of a cloud just below TC. So this little higher density in the middle, that's a BEC just starting to form. And this is the momentum distribution of a pure BEC. They don't look terribly different, but yeah, this one's a little narrower in momentum. This is the signals you get from doing experiments with these 3 different. So if you blow up the signal by a factor of 2 and you really squint for this thermal distribution, you can see, there's a little bit of a wiggle, right? Atoms are still quantum mechanical, they're still waves. It's just every atom's doing its own thing. Just under TC, you start to get a BEC, and suddenly you don't have to multiply a signal by a factor of 2. You can see the oscillations, pretty clear. Make a pure BEC, and wow, okay, we've got huge oscillations, really easy to measure. We can measure them very precisely. And bear in mind, this is done by evaporatively cooling, so the atom numbers are about the same in all these pictures, but if anything, this one has a bit fewer atoms, dramatically bigger signal. And so that's where BECs really make a huge impact on how we make measurements in the lab. And just to show you, we did get better at controlling our atoms. This is from one of the data runs that made this data. You can see each atom is in a superposition of very well separated positions. Okay, is it here, here, or here? And the answer has to be it's all 3, because if it's not in a superposition, you don't get these interference fringes. So this is totally key. The fact that it's a bunch of atoms in a BEC, you might lapse back into thinking, yeah, a third of the atoms are here, a third are here, and a third are here. No. Every one of those atoms is in a superposition of all 3 places, because if it weren't, we wouldn't see this interference at the end. Okay? We just have blobs overlapping at the end. Okay. Great. Last thing I want to talk about is superfluidity. So a BEC, turns out, is also a superfluid. Now, superfluid is a fluid that flows without resistance. Okay? So you may have heard of a superconductor, which is a thing that allows current to flow without resistance. A superfluid is a fluid that itself can move around. You can pour it through some channel, and it will flow without resistance. You can drag something through it, and it won't experience any resistance. You could say it has no viscosity. And basically, a superfluid is a macroscopic wave function. Okay, so it's something maybe I'll even say this the other way around. People discovered superfluidity in the early 1900s, long before we had made BECs in the lab. And they figured out the only way this thing makes sense is if it's secretly a BEC. Okay. So in a superfluid, you have a macroscopic wave function, just like the BEC wave function that we talked about. Say it in reverse, a BEC is a superfluid. And one of the neat things about that is if you rotate a superfluid, right, up to a certain rotation rate, nothing happens. Why is that? Nothing happens because if you measure the phase of that BEC wave function as you go around in a circle, it had better come back to the same phase after you've gone around the circle. Otherwise, your wave function would have multiple values. This is a very bad thing. This should not happen. Okay, so if I go around this circle, I can pick up no phase change. It can just be constant phase. That's what happens if I don't rotate it. If I start rotating it at first, it'll stay constant phase. Nothing can happen. When I hit a critical rotation rate, suddenly this will become 2 pi, right? So the phase will increase, and we'll get to 2 pi, which is the same as 0. So the wave function isn't multi-valued here. But it does have a phase gradient in a circle. And hopefully something that you learned in quantum mechanics is that a phase gradient in a wave function corresponds to a current or a flow. Okay? So if I have a wave function and the phase changes linearly across it, what that means is my particle is moving at a constant velocity. Okay. Here we've got a phase gradient around, which means it's rotating at constant velocity. But a superfluid can't rotate at low rotation rates, and then suddenly when you satisfy this criterion, it can rotate. And the way it manifests that rotation is it forms a vortex. So this vortex is a place at the center with 0 density, right? The density drops to 0. And then around it, you have this flow. You can see this in the lab. So if I take a BEC and I stir it, I start rotating it, won't have any vortices at all. It won't respond at all until I get to a certain critical rotation rate, and then a vortex appears. And if I rotate more, a second vortex appears, and a third vortex appears. Now you might think, hey, wait a second, shouldn't it just be a vortex that gets faster and faster, right? It was 2 pi. If I rotate harder, maybe it goes 4 pi. Turns out, and this is more complicated and again has to do with interactions between the atoms, the energetic cost is lower to make a whole bunch of single vortices than it is to make one super vortex. So, there's, I don't know, about 20 vortices in here. Each one of them has a 2 pi phase winding as you go around. So there's a localized little flow, but there isn't just one big one in the middle with a 40 pi phase winding. And this continues. You can spin these guys up and have hundreds of vortices up here. And you notice something. These are packed into a triangular lattice. This again is due to interactions. Basically, the lowest energy state for all of these vortices is to form this tight packing crystal. Now, one thing which we'll talk about more in the next lecture is there's a connection between superfluids and superconductors. And so one reason to do this experiment is super cool. Look at that. The vortices align, they make a lattice called an Abrikosov lattice. You can see waves undulating through that crystal of vortices if you work hard. Lots of cool stuff, just fundamental physics stuff. Because this is analogous, and analogous in a very rigorous way, to a superconductor with a magnetic field through it, we can actually take experiments with ultracold atoms and learn things about superconductors. So a superconductor, it turns out, is just a superfluid with a charge. And so this idea that I can say, I I played with some atoms in the lab, and it actually taught me about superconductors, which are technologically quite important. This idea we're going to talk about a bit more in the next lecture. The next lecture, we're going to do sort of the same thing, take a look at what is done in modern ultracold physics labs with degenerate Fermi gases. And one of the themes there will be this idea that I can take a cloud of atoms, which I have incredibly precise control over, cool it down, and it will act very analogously to the electrons in a metal or the electrons in a semiconductor, right? We can do different things to them to make them act like different systems. And this all goes under this heading called quantum simulation. So we'll talk about that more in the next lecture.